Welcome to video 3 of 4. So now we're going to use the fact that enthalpy is a state law to describe an interesting way to figure out reaction enthalpies. So take, for example, this reaction right here, the conversion of 3 molecules of oxygen gas to form 2 molecules of ozone. And let's say that you were interested in what the enthalpy change of this reaction is. So this is a very important reaction that occurs in the upper atmosphere. That the production of ozone is important because ozone actually protects us from a lot of ultraviolet radiation from the sun. So it's good to have it in the upper atmosphere. In the lower atmosphere, it's not that great because it's not the best thing to be breathing. So let's say you were interested in the energetics or the enthalpy change of this reaction. Now it turns out that some reactions, getting a delta H for it experimentally directly can be notoriously difficult. So sometimes you can get at it in a roundabout way. So I would give you this information right here. Reaction, calling this reaction 3A. So 3 moles of oxygen reacts with 4 moles of solid boron to give us 2 moles of B2O3, so diboron trioxide, if you remember your naming rules. And reaction 3B, which is the reaction of ozone with boron to also form boron trioxide. And it turns out that if you have this information, you can use this to determine sort of a roundabout way of running this reaction. And so the first thing I want to ask you to do is think about how you could manipulate these reactions in a way that they add up to this one. And by manipulate, I mean you might have to flip one of them around. You might have to multiply everything in one reaction by some factor, double everything, half everything, in a way that when you add them up, you end up with this reaction. So let me give you some hints as to how to do this. What you want to do is look for components in this. I call this the target reaction. So usually I write it down at the bottom because it always seemed to make better sense. I can visualize it better that way. Look for components in the reactions that you have to play with that are only present in one place. So for example, O2 is involved in your target reaction. And O2, in both of these reactions, O2 only occurs as a reactant in reaction 3A. So that's a sign that maybe you should leave that one as is. And now think about amounts. This reaction requires 3 moles of oxygen as a reactant. This reaction has 3 moles of oxygen as a reactant. So maybe you just leave that one as it is. So 3O2 plus 4 borons gives us 2 BO3s. Now, B2O3, I'm sorry. Now, since I did nothing to this reaction, the enthalpy change is the same. It's negative 25, 28. And this, since I didn't change this, I'm just going to still call this reaction 3A. Now, look for other species. So there's the ozone, right? So the ozone in these two reactions right here is still only found as a reactant in reaction 3B. You need it as a product, and this is the only place you have it. So that's an indication that you're going to have to flip this reaction. And the other thing to think about, if you hear that in the background, that's the dogs barking at someone with squeaky brakes. So you need to get the ozone, and also the fact that you have 1 mole of ozone in this reaction. You need 2 here. So this tells you that you're going to have to flip this reaction and then double it to get the 2 moles of ozone that you need. And that is going to look like this. So now I've got 2 B2O3s. I'm making 2 moles of ozone, and I've got 4 moles of boron as well. Now, what's delta H for this reaction? Well, it is not negative 1406 kilojoules, because we have doubled it and we've also flipped it. So if you remember back from possibly a couple minutes ago in video 2, now we know how to manipulate that. We know that if we flip a reaction, you just reverse the sign on it. And if you double the reaction, you double the heat. If you half everything, it halves the heat. So we know from that. So this is, I would call this -2 reaction 3, because that means I flipped it and I multiplied everything by 2. And this is easy because this tells me exactly what I have to do for this number right here. I need to change the sign and double it, which means that the reaction, and again, I would say ignore this negative sign here. So we're just going to scrap that out here. So the delta H for this process is positive 2812. And I would encourage you in problems like this to explicitly put in positive signs, because you can get into trouble if you're trying to subtract something, and sometimes it's hard to propagate the signs if you're subtracting a negative unless you explicitly put everything in there. Now let's look at what happens when we add these two reactions together. Well, if we add them together, the borons cancel out, the diboron trioxides cancel out, leaving us with 3 oxygens, giving us 2 ozones, exactly our target reaction. And the rule is that if these reactions add up to this, then these enthalpy changes have to add up to the enthalpy change of this reaction as well. So whether you converted the oxygen directly into ozone, or whether you took this roundabout way of reacting it with boron to make boron trioxide and then decomposing the boron trioxide to make the ozone, the overall energetics have to be the same. So if these reactions add up to what we care about, then these enthalpies will add up to the enthalpy change for the reaction that we cared about, which means that that process is endothermic by 284 kilojoules. Now, I would also perhaps have given you another one to work on in that group activity, and this is actually the one. So this is the reaction that is used in some smaller rocket engines. Usually it's the rocket engines that just kind of move something, that do minor directional changes, not for the main thrust. This is something called hydrazine, sorry. And when it reacts with hydrogen peroxide, forms nitrogen and water and gives off quite a bit of energy. And your task will be to use these 3 reactions and their associated enthalpy changes to tell me what delta H is for this. So do try this. I will tell you that this is about as complicated as any of the exam questions on this topic is going to be. So if you can do this one, you should be fine. So hit pause, give it a shot, come back, and tell me if you got negative 818.12 kilojoules. So I told you it was a rocket motor reaction, so you should expect it to be pretty exothermic, and in this case it is. And the manipulations are that you have to flip the first reaction, you flip and double the second reaction, and double the third reaction. And another thing to note from this is liquids and gases in this context are not the same. So they don't cancel each other out. They specifically have to be the same thing. So let's see, where is it? Right. And so again, if you can do this one, you're in good shape. So make sure you practice to get to that point. And I will see you at the next and mercifully last video.